welcome to the AOS seminar. Today we have a speaker, Dr. Mingfang Ting. Mingfang got a bachelor's and master's degree from Beijing University. After that, she went to Princeton University and got her PhD at GFDL. And then did a postdoc at University of Colorado, Sirius. Before joining the University of Illinois at Champaign. She stayed there until about 15 years ago, and then decided to move to Vermont, where she stayed for the past 15 years. So apart from research and teaching, Mingfang also is the director of the Climate and Society master's program at Columbia. And obviously, what she's talking about today is very crucial, and very relevant to climate and society. So let's welcome our speaker.
Thank you very much, Edmund, for that introduction. Edmund and I, of course, met at GFDL. He ignored that part. I don't know why. So we've known each other for a long time. Mentioning about climate society, that's actually interesting because I think we must have students coming from Stony Brook in the past, but I know this year definitely one undergrad student graduated from here came to our program. So it's nice to you mentioned that program. So yeah, I'll be speaking on heat waves and drought, mainly in the southern part. And really, it's two different topic, but I kind of think they are linked in some way. So I'll see how much I can get through. And I want to mention the collaborators because I really can't do all that work myself. This Chang is a visiting student from China. He is very productive and did quite a lot of work on the second part, the heat waves. And of course, I work with Richard Seeger and a whole bunch of other collaborators at Lamont on drought-related research for many, many years. So this is part of that big group effort. I guess I have to do this. Okay, I'll just use a hand. And it's kind of like in a day like today to talk about heat waves and drought is probably a little bit not quite timely. Hurricane would be more timely in the situation, but this past summer, I think we've seen quite a lot of headlines talking about heat waves, and I'm, just randomly putting out here this, high temperature in southwest, up to 110 degrees in some parts of California, and then the wildfires that we've seen a lot. I mean, this is just one example. So all of that are, of course, related in some way. But what's more interesting this year, I think, is the heat wave is really covering everywhere. Northern Europe, Asia, Japan. So it's really becoming a question of whether we're seeing sort of exploding of this type of climate change related phenomena. But what I'm going to focus on is rather than just talk about how much is due to global warming and how much is natural variability, I'm trying to focus more in this talk on the mechanism. So if we understand mechanism, then we can probably tease out a bit better in these way. And speaking of the drought, I also wanted to bring the current U.S. drought condition. This is the U.S. drought monitor showing the Southwest is still under pretty severe drought condition. The red and the dark red is excessive. I think they are like exceptional drought. So we're in quite a lot of the region, like the Four Corners here, is in the exceptional drought condition. And California is a little bit better, but it has been in drought condition. I have another slide showing the California region. And interestingly, when I was putting the slides together, New York Times had this article on Sunday, the past Sunday, about the Rio Grande is drying. Does anyone care? It's an opinion piece on the Sunday newspaper, and showing this the Rio Grande is really drying up. the stream flow is lowering. And of course, this article is actually talking more about water rights and things like that. But I think it's ultimately it's related to the reduction of availability of water. So it really is a very severe kind of issue that we're facing in the Southwest at least. And speaking of California, I wanted to bring this up to show how long it's been in the drought condition. This is showing the drought area in California in different color, again representing different category of drought. And you can see this recent decade or so, a little less than a decade, has been in this really severe drought. And it's showing here is the map of California. So you're calculating basically the area coverage and in percent. So it's almost 100%. In the past few years, it's 100%. Now we're kind of coming down. This map doesn't cover the whole period. But within this period of very, very severe drought, even the 2015-16 El Nino didn't break it, which of course partially because the El Nino didn't produce a lot of rain in California, but also because the drought is really so severe. And only I think it got broken by the 2016-17 winter when we had a lot of rain. So that was the reason that now we see the drought map is not as severe. So all of these are basically begging the question of what is the cause of all of these drying conditions? Is it simply just because global warming and temperatures rising, or there are more to it? Or do we really understand it? The mechanism behind all of these. So also this is not a new problem. And this is a paper I wanted to bring up. We published about now over 10 years ago in Science, led by Richard Seeger. And we're looking at actually the CMIPS 3 set of models. And I don't think, even though now we have CMIP 5 and then soon we'll have CMIP 6, I don't think this picture's changed much. So you can see that at that time we were already looking at P minus E, so the surface net heat, water flux. In 19 of those models, averaged over southwestern U.S. And you can see the precipitation and P minus E, I think there's precipitation and P minus E, all going down. So it's already been kind of projected to do that. But again, the question is it, what is the actual direct cause in terms of our, with atmospheric science background? We should be able to tell what is the cause of it. And here is the observation based on recent period, 1980 to 2010. And it shows that reduction in percent of precipitation in this region that, of course, covered the area, covered the region that we just talked about, recent drought and California drought. It's all included in that. So clearly, we're seeing it already, and we're projected to, the models are going to, models are telling us this is going to get worse and worse. So the question is, again, how can we answer, the question of what exactly is causing these kind of drying? So I guess at least there are a couple of questions that I wanted to address. One is, why is the Southwest U.S. getting drier in recent years? And can we, actually pinpoint a mechanism to it? And secondly, what is the seasonality of this drying? Is this drying mainly happening in the wintertime or summertime or throughout the year? So that's another question I kind of wanted to touch upon. And again, what are the physical mechanisms? And this is a paper recently published in Journal of Climate. And from the title, you can see it is the spring drying that is the most prominent. There are other seasons drying too, but we find spring is the season. And then if I have time, I will try to cover a bit more on the heat wave side, because it is really such an interesting topic, especially after the summer. In this case, we'll be focusing on in Texas region, in the southern U.S. region. And the question here is whether we're seeing more and more extreme heat waves in the U.S., and if so, why, and where are we seeing the trend? So again, I hope I will be able to get to it, but I always put in too much in the talk, so I might not getting a lot of details when we get to the second topic. But feel free to stop me anytime, because I might talk too fast. So let's focus on the first question about the drought in the Southwest. So this is motivated by a study published in 2014. They're looking at various model projections. WRF is the regional model, as well as the CCSM4 and some of the multi-model CMIPS. These are the same plot, except that they're using different way of characterizing the significance. So what this one does is it shows that spring season, this is throughout the annual mean, as well winter, spring, summer, and the fall. But in the spring, you can see this Southwest region is the one that seemed to be very robustly, no matter how you define your significance, you're able to see that there is drying persistently happening between these two periods. It's the end of the 21st this century and end of the last century comparison. So that got us thinking about what causes this spring drying, intensified spring drying. Again, you can see some other regions, in the summer as well, they are drying, but it's not as clear. And this also seemed to be consistent with observation that shows the pattern of drying in the spring. I mean, this is for annual mean observation, but it seemed to match pretty well with what model project is going to happen. So motivated by that, we wanted to understand the spring drying, what causes the spring drying. So before I get to that, we actually started looking at the climatology in terms of precipitation. It's not something that even though we talk about U.S. precipitation patterns all the time, but it wasn't that clear when you go to the regional scale. So obviously you can see, throughout the season, you see this Pacific storm track brings in precipitation to the West Coast in the winter time, and then the Atlantic storm track kind of starts, brings a lot of rain to the east and southeast. And in the middle is relatively dry. But if you focus on the Southwest, there's a big outline here. It gets sort of winter precipitation gets from the northern part. And then the south is relatively dry throughout. And as it gets to the spring, this winter precipitation reduces slightly. And then you get to the summertime, you have the summer monsoon, North American monsoon. So it's actually a very, very complex system. Over the entire region, it's not completely uniform. So to be able to see this uniform kind of drying is kind of interesting to us. So what we really care about, of course, is the P minus E, so the net water flux at the surface, not only the precipitation. So when you look at the precipitation, if you average over this box that we just talked about, this Southwest box, precipitation does, peaks in the wintertime and slightly goes down in the summer, but the seasonal cycle is not very large. But when you're adding the evaporation, because it evaporates a lot in the summer and less in the winter, so then it shows the net surface water flux, P minus E, is showing a very clear seasonal cycle. This is error interim, which is also what we showed from previous ones, the error interim. And compared to the multi-model CMIPS seasonal cycle, actually it's depicted pretty well in this case. So you can see that climatologically in this region, it's the summer that depletes the water, and in the winter that replenishes water for that particular region. So then we wanted to first understand what causes this summer minimum. Again, it's not a P, but P minus E, so the net heat flux, net water flux at the surface, so that is related to how much water is brought into the region, right, by atmosphere. So the convergence, column average integrated convergence of water is equal to P minus E. So we kind of go from this angle. So first, let's understand what causes the minimum P minus E in the summertime, and hopefully we can understand from that then going into the change of P minus E between future and the present. So let's first look at the causes of summer drying. This is again climatology. And the tool I'm going to use throughout the first part is going to be using the moisture budget analysis tool, which is basically, as I mentioned already, P minus E is the net influx of water to the ground, to the surface. is equal to the convergence of total atmospheric water vapor, column averaged, brought into the region. It can be divergence, then that'll be drying. So if we, as we do, we usually take a monthly mean so that we can look at the process slightly separately. So in this case, monthly mean P minus E is equal to, this is the mean part of the moisture convergence. So these are caused by the bar product, where bar is the monthly mean. And the part that is sub-monthly, the transient part, the eddies, are also fluxing moisture, bringing moisture in and out. So these two processes can be separated in this way, which is very standard. And now we're going to focus here on the mean moisture transport. The transient part you can't really further separate into anything. So we're going to further separate the mean moisture convergence term here. And I ignored the constant here, the 1 over G rho W part. So if you just look at the varying part, so this is the mean moisture convergence, and that can be separated into three terms. One is the moisture advection term, so the flow is advecting the moisture gradient, delta Q, and then there is also the mass divergence. So mass convergence or divergence without the moisture, it's a uniform moisture. If you have mass convergence, it's going to bring in moisture, or divergence will take the moisture out. And then a term we call the surface term, which is basically because of the surface pressure change in this integral, so that you end up having a separate term, which turns out to be kind of a bothersome term because it's hard to interpret it. It's just because of topography and things like that. So we call it a boundary term there. And I'm not going to focus too much on that term, as you'll see. So now we're going to further focus on in the later on. So if we want to look at the change in moisture, then we can change in moisture. That budget is can be further separated. Delta of this term is delta of this term and delta of the transient. So the mean and the transient. And again, these can be separated into several terms. This term is the mean one, so the changing mean can be separated into the change due to circulation change. This is the delta U change, or the change due to delta Q. So again, we sometimes call this one dynamics term, and this is a thermodynamics term. So that's going to be used when we look at the spring drying. Oops, sorry. So that's the first change is dynamics, and this is thermodynamics. So we can separate in that way. This is going to be the only slides with all the equations. So I won't be, they'll be appearing in slides, but I won't be focusing on that. So that's the framework. I'm going to kind of try to tease things apart and understand the physical mechanism of the drying. All right, so back to the seasonal cycle. So the question is, what is the cause of summer drying in this region, in the southwest region? So what we did here is, again, T minus E, we've already seen that, the seasonal cycle from January to December here, the months. And now we look at each of these terms. First of all, we have separated the P minus E, which is total moisture convergence, into the mean part, again, in the error term in CMIP5. And so the mean term shows slightly different seasonal cycle, but you can see that the summer is not, it's not really the most drying season in terms of that. And then when you add the transient is drying the summer season, right? So that's an important part. And then when you further separate the mean and the mean into the advection and the mass divergence, interestingly, that is actually the one that, the mean due to the advection term is the one that is very important. So especially for the spring period here. So what we are going to focus on then is going to look at what is really causing this drying due to the mean advection term, which is somewhat surprising to us when we first saw this result, because we were expecting this term, which is the mass divergence term, because this is Southwest U.S., as we know, is in the region of subtropical high control. So a lot of us, teach undergraduate class. We always talk about that region's dry because of the divergence, mass divergence region. So when we look at this separation, we actually find this term is not as important. It is drying, but it's more of this. But you can also notice that there is a big boundary term there. So the boundary term may be something that averages out. So first of all, I'm going to kind of ignore the transient contribution here, even though it is important. It is dry in the region, we know, in the summertime particularly, but in the wintertime and spring is actually wetting, so it's fluxing moisture into the region. So what I'm going to focus on is the drying caused by the mean, which is focusing on the advection mechanism. Yes?
Just by I couldn't see why B minus E. If you had to mark this, definitely not considered. Are those rivers?
You mean comparing these
by
two?
Area, yeah, it should be 0 area.
Throughout the season, you mean?
No, integrated over the year. It's definitely positive area.
Yeah, there is definitely a wet bias. I think you're right in the model.
In the models,
yeah.
Where it goes, rivers.
Yeah, I think so. Yeah,
But
it runs.
Big,
yeah, that's true. You notice that. Yeah, there is an average across the year. It is a positive amount. Right. Yes, we actually later on sometimes we'll have to do a little correction to it. Yes, the model tend to produce more rain.
Model's supposed to compute exactly. It's not observation.
What's that?
Model should compute exactly.
In terms of the water balance throughout the year.
They should conserve water.
Not yeah. There's
So that was the only thing that I think of is rivers.
Yeah. The models can do anything to the excess water, right? Yeah. But yeah, thanks for pointing that out. I forgot to mention that model does have some kind of wet bias in this case compared to the observation, and we're going to focus on the model, so that is an important thing to keep in mind. So yes, we're going to focus on this season and then focus on this term, mean advection term. So the next question is, why mean moisture advection cause drying in southwest U.S.? Because if you imagine thinking about ocean atmosphere, ocean land configuration there, mean advection there is westerly wind. It should bring ocean moisture into land so that it should be moistening rather than drying. So what we're going to do is we're going to look at the U and then look at the Q just to get an idea of how climatologically they are lined up so that it produces actually drying.
So I have a question.
Yeah.
When you look at the boundary term, it kind of balances the mean moisture advection term. So how come you
Yeah.
what led you to think it's this term which is causing drying?
Yes. So what you're saying is these two seem to kind of cancel. Yeah. I mean, okay. So we can't do anything about the boundary term, but because that is mechanism-wise, it's just because of topography. So what we are thinking about is in terms of the mean, these two terms both contribute to drying, and in the relatively speaking, this is the term that's dominant. So yes, I agree with you that is an issue. But the reason we focus on this, actually, we went the talk went backward, but we were looking at actually spring drying first. So the spring drying is mainly related to the advection term. So that led us to try to understand what the advection process is doing in the climatological sense. But yes, it's a caveat that we have to keep in mind that there is this opposite sense. I mean, there's no reason to believe this cancels that also, because it really cancels both of these terms, right? So in terms of the relative importance of these two, it still is the mean advection. So that's what we are arguing in this case. But I totally agree, because in that region is complex mountains and stuff. So it's the boundary term, the del PS term, is actually quite large, and it's an issue that we have to face in a lot of these kind of analysis. It's just a kind of an error term, or it's not. There are physical meanings, but it's not it's not clear how to interpret it. But thanks, yeah, for bringing that up. So we're going to look at the U field at a low level because moisture convergence mainly come from the lower level. And we're going to look at the Q and see how these two work together in order to cause this advective drying. I mean, even if the advective drying is not necessarily that important in this context, but still, it is a drying, so we wanted to understand why this is the case. So there are a lot of stuff on this one, but I'll point out the important thing that I wanted you to focus on. So here it's showing the 850 specific humidity, the Q bar, and averaged for different seasons, winter, spring, summer, and fall. And here is the vertically integrated mean moisture transport. So that wind is integrated into this plot here. It's a little bit hard to see the arrows. It's too small, but I'll try to walk you through. So what you can see here is that in the west here, in the west coast, it's mainly dominated by this anticyclone, so anticyclonic circulation. So the air, the moisture transport at least is coming from in the coast. It's coming from the north. So it's this kind of circulation here. So what you end up is having a minimum in specific humidity along the coast. So it's not actually because of the ocean so that you have high humidity. It's actually a minimum in moisture content, particularly in the springtime and the summer as well, and winter less so. And then the moisture transport over land in this box here is actually, I have a little arrow pointing, so it's actually coming from the ocean toward the land. If we focus that, and it's a little hard to see the white arrow that I try to show. So the moisture transport here is in this direction. So you can see it's directing exactly this moisture gradient, so bringing relatively dry air into the land region, rather than the moist kind of, in our mind, it's moist air from ocean toward land because of the anticyclone, the oceanic anticyclone there. So it creates this gradient. It's temperature-wise too. If you look at the temperature, I didn't show it here, you will be having a cool temperature, as we all know, in the west coast. So that is basically following moisture and temperature, both having a minimum along the coast. And then you have advection bringing into this cold and dry air into the land. So that is how that creates a negative or drying effect in the southwest region because of this advection term. So then we look at the vertical profile because that was just 850. So you can say, okay, maybe the moisture vertical profile is different. So here it's showing the same kind of error interim CMIPS comparison, but for the vertical profile, average over that latitude band of the southwest, and as a function of longitude. So now you can see the topography. So this is the coastal topography, right? The wide region, the missing data, and the green lines are showing the Q profile, the Q contour, the more specific humidity, and the black is the temperature contour. So you can see that this is taking out the zonal mean, so we wanted to bring out the asymmetry there. So you can see that it's cold and dry along the coast, and warm and wet over the land. And you also see this maximum in the Q is actually over on the other side, east side of the mountains, which is because in the previous one you can see this in the summertime you have Great Plains low-level jet brings in a lot of moisture from the Gulf that creates this local maximum. But overall, you can see this moisture is following the temperature contour, but showing this east-west asymmetry in the sense that the west is cold and dry, and the east is wet and moist. So if you imagine the wind is bringing moisture into land is mostly westerly, then these wind will then bring cold and warm air, cold and dry air into the southwest region.
So it's not clear in the green line within the boundary layer, whether over the ocean it's larger humidity than land or not, because to the west there is this relatively low boundary layer in the bridge. troposphere, it would be dry. But
That's right.
below it,
Exactly. But it doesn't really matter too much because it is the vertically integrated that matters, right? So the gradient is there even as you go up. So right at the surface, yes, it's hard to tell because it's underground, over land. But overall, it is a gradient, east-west gradient there. So in the calculation of moisture convergence, that integrates the whole column. Yeah. Okay, so now we're ready. So we kind of understand why summer is drying in that region, partially because, there's the transient effect. The storm track moves further north, so that leave that region to be relatively dry. But additionally, there is this mean advection term that tend to contribute to the drying. So here we're looking at the changes, because that's really our purpose, is to look at how spring drying happens in the future. So this is for with the changing moisture budget terms in different periods, as you can see, different 2021 to 2040, 41 to 60, 61, every 20 years up till the end. So the different period of the future with respect to 1979-2005 average in the CMIPS model, multi-model. So first, let's look at the P minus E. So you can see the reduction in P minus E tend to be focused mainly in the springtime, right? So which is consistent with previous work already pointing out in this region, spring drying is the most robust and dominant process. In the summer, there are some reduction, but not as much. So if we compare to the climatology, so this is the CMIPS climatology. You can see that here, of course, the drying is mainly in the summer, and the spring is kind of starting to be dry. But now it's a large shift toward the spring, so you have more drying in the springtime. And then again, we do the same thing here. We say, okay, is it due to the mean or is it due to transient? The two parts. So in this case, the transient moisture convergence is the mean moisture convergence is definitely the one that causes it. Again, you can see why we focus on that, because the transient part in this case is actually the opposite. Transient is trying to flux more moisture into the region rather than drying it, but the mean is the one that causes really the spring drying. So that's, again, we will be focusing only on the mean moisture convergence and separating it into different parts and see how we can understand that drying due to the mean moisture convergence. So this is the difference here. And also you can see that in terms of time, I put in different lines, so it's basically getting stronger and stronger as the year goes. So it's, in that sense, it's also very consistent. So what causes this very relatively robust spring drying in the future? And again, bring back what we've already shown. So we're going to look at the changing moisture budget, and due to the mean, which is the focus here, that's mainly due to the mean, and moisture transit, the transient moisture part, the changing that part is actually contradictory. In the opposite sense. So that we're going to not look at that, and then we separate. In this case, we separate this into two parts: dynamic, the circulation change. Is it because of the whole circulation change in the region in the spring causes that, or is it because of changing moisture? So that's a thermodynamic versus dynamic contribution, right? So in this case, we don't have the boundary effect to worry about, because you look at the boundary only when you have to look at the advection term, separating the advection and the mass divergence. So here we're combining everything together. Okay. All right, so I think this is our the key result here. So now we're going to first look at the moisture budget, P minus E, the changing P minus E, which we already looked at earlier, and it's drying, right? And in the southwest, it's very much drying. And then you look at the mean moisture convergence. Sorry, it doesn't really come out that clear from the back. It's probably hard to see. But the brown color is the drying. So you can see that the brown here, so you can see mostly due to mean, and the transient is wet. So that's basically what we already see in the average sense. And this is just showing the distribution. So now we separate into dynamic, thermodynamic contribution. And you can see in this case, dynamics, it is dry, but not much. And it's all due to thermodynamics, right? So it's all, not because of circulation change, but rather it's the Q change that causes the drying. And we, again, separating into, I said too fast that I'm not going to look at the advection and the divergence. But if you were to separate into advection and divergence, and in this case, actually, because boundary term doesn't really change much, the del PS, so it's not a huge deal in affecting this separation. So when you look at the change, actually, these two add together pretty much reproduces the total. So the thermodynamics part, this part, can be separated into a advection part and a mass divergence part. So in this case, it says, okay, because it's all due to the Q change. So this is like, if you change delta Q bar, the gradient, that's what happens in this case. So it gives you more climatological flow acting on a stronger moisture gradient. And in this case, if you have the mean convergence divergence, but just delta Q is changing. So if delta Q is decreasing, you have convergence, then you will have a decrease in the moisture convergence, the mass divergence. And this term is very small, as you can see. So it is all due to the advection term. So again, that kind of goes back to why we focused on the advection in the climatological sense. And that also explains, in the beginning, we want to understand what is this advection term doing here. So we're going to focus on the advection term coming from this thermodynamics. And this is just showing the same thing averaged over this box, southwest box here. The region is not really a triangle sort of shape. And so P minus E shows, again, shows in different years. And this is just a one time. This is showing the end of the 21st century. And here we're showing 4 periods, so the near future in these two, and then far future in a sense. And so P minus is changing, is decreasing, and that's mainly because of mean moisture convergence from that. And then the transient is actually acting to oppose that. So transient is trying to reduce that, dampen that effect in the mean sense, that's what transient does, as we know. And then we separate into dynamics, thermodynamics, and dynamics almost nothing contributes. And it's entirely due to the thermodynamics, right? And then the thermodynamics, again, is separated into thermodynamics due to advection term or thermodynamics due to mass divergence. Again, it's predominantly due to the advection term. So the question is, what is changing in the Q bar? Why is the gradient in Q bar is changing so much that it creates such a large effect in drying in the spring season? This is all for the March, April, May spring season. So maybe I said too early that I'm not showing any equation. So there is another equation, but it's at least it's a very well-known equation. It's a Clausius-Clapeyron equation. So what we are thinking is try to understand this Q. What is the Q change? What causes the Q to change? And we can write. I think may not be entirely an equal sign. Maybe there's a slight approximation. So Q is this is without any. Q is equal to relative humidity times QS. Oh, but there is. I think I was pointed out by one of the reviewers. It's the E. E over ES is relative humidity, not Q over QS. So there is a small approximation involved, but I think this is pretty accurate. And then, because QS here is related to the saturation vapor pressure, ES, through the Clausius-Clapeyron equation, like this related to basically temperature. So in order to have the change in Q, you can either change relative humidity, right? Over land, relative humidity can change, as we've probably read papers talking about land relative humidity is actually changing, reducing, or because of the QS through temperature. So if your temperature change, you can change the QS. So we got to separate these kind of effect. So it's separating the effect due to relative humidity change and those due to QS through temperature change. And the temperature change here, we're going to look at either it's a zonal mean temperature change, the warming due to the zonal mean, atmosphere is all warming up, or it's because of the land-ocean contrasting temperature is increasing, intensifying. So that can be separated as well. So here is the further separation. So we are going to change the changing Q, which is future minus present, can be written in this way, which is either due to the change here, due to the change in delta R is the relative humidity change, or due to temperature change, and a higher order term, which is relatively small. Both delta R and delta Q are going to change, delta QS. And so it's approximate into, if you ignore that, it's approximate into the change due to delta R. So P is present, so P means you keep it at present value, or you keep the R in the present value, so not allowing the R to change, but delta QS change due to the temperature, which includes the zonal mean plus the asymmetric part of the change, which is intensifying land-ocean thermal contrast. Okay, so that's what we did. So you separate these, and then you calculate what the Q field looks like. So this is the model, multi-model mean, that we're trying to explain. This is the change that I haven't shown you, but this is how the model is changing in the sense that it intensifies the moisture gradient in the springtime. So indeed, you have this moisture gradient that we already see due to the climatological distribution of wind, as well as the land-ocean arrangement. And now you know that this is actually in the future is going to be intensified. So the question is, why is it intensified? What causes it? And we calculated using this equation here, this one. If you include both the change in delta R and delta T, the temperature change, you get pretty close to the actual, reproducing what's in the model. Now here you're just changing delta QS due to the total temperature change. And you can see that it's not a perfect match, but it matches pretty well. Even without the relative humidity change, you can pretty much reproduce what's happened. And it may be a little bit too strong. And adding the delta R, relative humidity change, you damp a little bit of that. And there's nonlinear term. So you add this and this together, you more or less reproduce this, except there is another higher order term that's being ignored. So we were able to really reproduce this total change by changing either the temperature through that, changing the QS, saturation rate, specific humidity, or by changing the relative humidity over land. And so it turns out that it is the temperature change causes the Q to change. And so we further separate into the zonal, is it zonal mean temperature change or the asymmetric one? And it turns out that the zonal mean temperature change is the main one that causes the gradient. Even though here you do have the temperature, the land sea contrast change, but that doesn't seem to cause a lot of the contribution, as we'll see, because the zonal gradient is not as large, so it's more or less flat across longitude. So here we are just trying to prove the concept a little bit more. We already know, okay, this is the zonal mean temperature change, which is great because zonal mean temperature warming up is a very robust feature in global climate change, greenhouse warming scenario. So here again, we are trying to predict this P minus E change using this equation. Changing P minus E is equal to this, and so here we're going to predict what the Q is going to be in the future, and so then we can calculate the total change in P minus E by using that change in Q. And so this is the GCM. And when we use the Q using this simplified way to calculate it, this is how we reproduce it if you take the Q change from the model. And here you're reproducing this by just calculating the Q based on the Clausius-Clapeyron equation. And so these are, or it's not exact match, but it's pretty closely matching what, ignoring all the other terms in the transient change and other thing change, you are reproducing pretty well using the calculated Q and the multi-model Q. It all shows very strong drying in the region. And then as we explained in the previous one, we can change delta T only. So only temperature change. Relative humidity is kept the same, and you can see more or less the same as the the rest. So everything comes from this. And then you can say, okay, what if I only allow zonal mean to change? And again, the match between them is very, very similar. So that shows that it is really the zonal mean warming that causes it. And the others are relatively small. So what it really says is that it's the even though it's kind of counterintuitive in a sense, because you have this zonal mean temperature warming up everywhere, and that actually creates a gradient in Q, because you would think the zonal mean is warming up over ocean as well as over land, so then it shouldn't create any gradient. But because of the nonlinearity in the Clausius-Clapeyron equation, so you have warmer land and colder ocean to begin with. So this nonlinearity is giving you the warmer land is the same amount of temperature change is going to bring up the Q more than the base temperature a little bit cooler, same amount of zonal mean temperature change is bring up slightly less. So it's very interesting that this gradient change in the Q due to the zonal mean warming is kind of causing the springtime drying to be intensified. And you may also wonder, then why is the spring only? What about the summer? Because summer is really strong gradient. And the reason there, what we see, I'm not showing here, is because in the summertime, the gradient is intensified, but the wind advecting from the ocean to the land is not as strong as the spring. Springtime wind is much stronger, the climatological wind. So that is why bringing the spring to the fall, sort of like springtime is really the one that shows this relationship. So it's kind of, we find it kind of a, yeah.
In this plot, did you already subtract the domain average? Because you would imagine when temperature increases, QS would increase everywhere.
Right.
So why you would have negative?
Yeah, because no, we didn't subtract the domain average, but this is because the term only comes from the gradient. So the globally increasing QS part, the baseline QS increase is not going to contribute in the advection term. This is only the advection term, coming from the advection term, right? So it is interesting in the sense because again I think it is a bit counterintuitive in the beginning, so that's why I find it quite exciting when I was working through this project, in the sense that we all talk about rich gets richer and poor gets poor kind of mechanism, which is basically based on a mean divergence change. So if you have mean divergence change, global warming increases the moisture, and then where you have divergence, you flux out more moisture. Where you have convergence, you bring in more. But in this specific region over land, obviously this is not applying necessarily over land, because mostly we talk about that mechanism over the ocean. But a lot of people think of southwest is the region where you have mean divergence. So that is kind of the natural mechanism. We started with that too. And we were just asking, why is it in the spring, not in the summer or other season? And it turns out to be that quite different. So this is just to summarize, sort of like a shift of P minus E seasonal cycle in the future. And here is, what you pointed out is this wet bias. So we actually corrected it using kind of bias correction. So it looks more averaged out, I guess, what you see. So in this case, you start with this kind of seasonal cycle in the current time, mainly summer drying. I mean, the changes are subtle. Once you add all the shifts into spring, you can see that, for example, this month, April, is getting much drier as the time goes, right? And summer is still more drying because climatologically it is more. But now you are getting less influx here. You have positive in March, but now you're reducing that. So overall, the March, April, May season average together is going to be a lot less water input into the region. So which will influence, like I showed in the beginning, the Rio Grande, the river flow. So the river flow comes from two things. You have the snow melt in the winter time, and then you have the input of water, from the season itself. And it shows that this is springtime input of water is going to be reducing. So particularly in the headwater region. And at the same time, we also expect the winter time become warmer, so the snow melt becomes earlier. So the winter influx of water is going to be quickly, either pouring rain or melt much earlier. So you can expect, as you go into the spring and the summer, the river is going to dry up. So that's what we are seeing in a lot of the, even now we're seeing that trend. So I think this just tells us, okay, because we know a mechanism that can explain this drying that is very robust across the model. Mean temperature drying, I mean mean temperature increasing, I think all of us can agree that is not something model will get wrong, right? So we identify this mechanism that is actually quite robust in the model, and that is contributing to this drying. So that is kind of the main message from this study. Through mechanistic understanding, we can say, okay, the models are probably telling us the right thing about the drying in the springtime being intensified. So we are going to see this, happening quite a lot. All right, so how am I doing in time?
It's about
Pretty much on it.
About time? Okay. All right. So I guess I won't have a chance to talk about my second topic. As I said, I always put in too much. I feel like I can cover, but I can't.
Come next time.
Yes, I'm so excited about this heat wave thing. I wanted to kind of talk about it, but yes, I can individually talk. I've already mentioned to a few of you about that project.
I have a question.
Yes.
Thank you so much. So you, as you mentioned, so spring drying is has already taken place in the Western US.
Yes.
And then when using the models for future use, they found this mechanism.
Yes.
So then this mechanism due to zonal mean warming should already be present in reanalysis for the recent years. Is it?
Yes, absolutely.
So you can show them.
We didn't look at the reanalysis period for this study because we are basically using the CMIPS model to do it for the reason that we wanted to identify this mechanism within the model.
But in observations, this has already taken place, right?
Yes.
So then this mechanism can be easily verified in recent observations.
We should. That's a good point. But I think it's going to be a recent observation like from 1980. You have like 30-year some period. You see the precipitation change. P minus E is changing. Right. So the mechanism will be a little bit more difficult to identify because of the natural variability is happening.
So like the zonally average temperature
Gradient.
gradient.
Oh, that's zonally. Yes, absolutely. Okay, you're talking about that. Yes, the robust part of it. Yes, you can identify the zonal mean temperature increase in the region. Yes.
So analysis is not observations.
Yes. Okay. Based on the reanalysis, you can see that in the recent period. Even the
knows what actually E is. P is easy.
P is easy. Right. But that's why you look at P minus E, which is mostly related to the atmosphere.
No, but the analysis is they basically run from the conditions and run for a couple of days. Then they change initial conditions, run again, change initial conditions.
Oh, right.
There is no consideration of anything.
The constraint, yeah,
Yes.
right. But I think you're right. If you just look at the temperature itself, you should be able to see that. But I haven't done that. So, yes.
Yeah. So yeah, you briefly mentioned summer, but it's actually interesting that actually not just that it's weaker, but it's actually opposite sign. That in summer.
Oh, in the summertime? No, it's not
No,
opposite.
in your change, in your separation into mean and transient, I think it seems that transient give rise to the change.
Oh, I see what you mean.
If
Yes.
you give rise, look at the change,
I know what you mean. Yeah, let me
Yeah.
do that. This one,
yeah, it's
right?
this one, yeah.
Yeah,
Because
right.
your mean actually give rise to increase in
This one here.
convergence that sort of offset the
Right,
transient.
right. Actually,
So if you look at that, that seems to be something that because it's opposite to
right.
the spring entirely. So
Good.
that may be something
Very,
that-
very good point. I think I answered your question. We didn't focus on this period for the total mean moisture convergence, but we did look at the advection part. So the advection part is drying, but not nearly as strong. So I think the fact that they are opposite shows me that it is probably the mean the mass divergence convergence in the summer is causing that. So it's different mechanism here. And also there is the monsoon, North American monsoon, that could contribute partly because the monsoon is a convergence, right? So if you have mean convergence in the region, that actually could increasing moisture itself can cause more convergence.
So I have this question, again, T minus equals more.
Why? T minus E is the essential thing.
If you look at this, the biggest change, which is like late 21st century, in December it's minus 0.2, but in January it's now plus 0.1 only. It just jumps. Oh, it should be periodical function.
Like here versus
Because
here?
in December. No.
Oh,
to the right,
December.
no.
Here. Right.
What that?
I see. Yeah, I mean, that's what the model says. Yeah. So December, you are saying December to January. You think December January should be more or less the same?
No, but not that jump.
Right, I agree. Yeah, that's true.
But
That is.
say from September to October, it's the same jump.
Where?
So if it's just because you only have 12 data points.
No, yeah, I mean this dashed double dot point.
Yeah, I know what
In
you
one month,
mean.
yes,
This
it's
one.
horizontal, and then
Yeah,
it
that's a
jumps.
pretty big jump. You're right. I didn't. Yeah.
I would check.
You can
I would
still
check that.
draw the curve up. I think that's probably okay.
Right. If I put a January repeating again, so it basically just goes back. Yeah.
It's the mean. It's mainly the mean that is jumping. So
Right.
essentially, there's a big jump just from the mean.
That's true.
Negative
That's
to
true.
positive.
Yeah.
So maybe it's possible that something happens around New Year.
It's not. It is a monthly average. So if you have monthly average mainly in late part of January versus the monthly average dominated by the first part of December, that's a pretty big difference. Because as Mingfang mentioned, it's only 1 point for each month. So it really, in this case, you wanted to look into maybe
But I think it would be very
sub-monthly.
interesting if it's real. Very interesting what is here.
Right. What causes the jump? That's okay. Good. Yes.
Yes, so you explained very well the zonal mean temperature increase leads to more moisture increase over the continent.
Yes.
Right, and that,
Exactly.
I think there is another very important element that is in the mean relative humidity distribution. You have dry to the west.
Yes.
And so even if you raise the delta QS the same, because it's dry. So R plus multiplied by delta QS is small on the right and left. So if you use the zonally averaged relative humidity, then you won't see as much impact. I think this mean relative humidity probably plays.
But I'm not using the mean for the relative humidity change. Relative humidity change, it has the structure included.
Yeah. So I mean, it's the structure of the relative humidity that also is very
contributing to this.
Important.
Okay.
In contributing to this, it's like even if you raise the same delta Ts, even the continent temperature and the ocean temperature the same. If the relative humidity is lower, then the moisture increase
more. I thought it would be the opposite if that's the case, because land relative humidity is lower than the ocean relative humidity. So the change would be opposite.
It won't be the case above the marine boundary line because that area is very dry, right?
I see. We didn't look at
You
the.
showed the specific humidity is very dry.
Right.
And
Right.
that
The R,
would translate to R.
Right. We didn't look at the relative humidity distribution in terms of east to west.
Yeah,
That's
my
true.
guess is that probably plays as dominant role.
Okay, so I'll look
Yeah,
into that. Yeah,
that's right.
yeah, yeah. And
So, I'm sure the model has biases in wind and also in ocean. How much does the model bias, estimated bias impact ocean water quality?
yeah, Well, definitely models are not going to give us, like the whole P- cycle is biased to wet. But I think in terms of looking at the change, because you're looking at both the present and future are within the CMIPS model. So the hope is that the biggest bias is going to be taken out. Unless you have reason to believe the future bias is going to either increase or decrease, then you look at the difference, then that should reduce the impact, right?
My question is actually very similar. I would assume that the moist bias or the wet bias is because the CMIPS models don't have accurate terrain, right? So the Sierras deplete 70 to 80% of the moisture coming into the Southwest, especially during the cool season. Downslope and dynamics. So,
right.
So in the back of my mind, I'm also thinking about that effect, which is clearly, I think, a winter problem and why it's too moist over the Southwest.
Yeah.
Because there's too much, moisture.
Summer too. Summer is not as dry.
So I'm wondering the fact that the CMIPS models don't have the terrain right and the drying attached to that, how that could impact it.
Yeah, it's a very good point. But when we looked at the vertical profile, when you take out a zonal mean, you look at the temperature and the humidity across two regions, it actually looks quite realistic. So, I mean, yes, we're comparing to reanalysis, which is not observation either. It's not a product too. But it seems like I totally agree with you. I think it would imagine the terrain in the CMIPS model is terribly represented. So you wouldn't see this kind of the mountain or the land-ocean contrast being shown up. But the models are actually capturing quite well this asymmetry, at least, a specific feature. Yeah. But I think you're right. Wet bias could largely be due to the terrain not being represented.
Okay, yeah, that's a good discussion. So let's continue that over lunch. So let's